Our second presentation is SMPTE ST 2110, the new standard Superpower. Our speaker is Lee Whitcomb of Imagine Communications. Lee is an architect for Imagine. He participates in SMPTE, VSF, and AIMS standards committees, including active involvement on ST 2110 professional media over managed IP networks, the ST 2022 family of standards, and 2059 Genlock over IP. Lee is the chair of the Toronto SMPTE section. His other affiliations include VSF, IEEE, and the Professional Engineers of Ontario. He holds a bachelor's degree in computer engineering from the University of Waterloo and a master's degree in electrical and computer engineering from the University of Toronto. Lee is the co-inventor of several patents in the area of timing and synchronization, and today he was inducted as one of the newest fellows of our society. Please welcome Lee Whitcomb.
Okay, just a question to start off here. So how many people are familiar with 2110? Okay, and how many people think they're experts in 2110? Okay, good. So today I'm going to sort of go over what's required of a standard and sort of take a look at what standards we have today and sort of how they don't meet the requirements, get into what 2110 is, what its current status is, and then you can sort of make the decision if it's sort of the new superpower of standards. So what are sort of the key applications that are being addressed here? So we're looking at sort of live production, could be sports, could be news type stuff, live play out. So live is sort of a very important aspect of what the standards are trying to look at. And these aren't all the applications. These are some of sort of the key ones that we want to sort of focus on and make sure that we've got all the requirements for. Needs to be able to support things like HD and UHD, support different frame rates and sort of mixed formats at the same time. So these are things that we're sort of looking for like sort of future applications. So to be able to address those applications, what are the requirements that we need to make sure we achieve? So we want to have our audio, video, metadata in separate essence flows. That way we can do things like breakaway audio. We can have, say, a closed captioning device that just outputs closed captioning, unlike today where it has to be connected with video. And so yeah, we want them to be separately routed and processed. Because we split them apart, we have to have a way that we can make sure to align them so we don't have any lip sync problems. We want to base these on open standards. We want to use standard off-the-shelf switches. We need to support UHD and sort of future formats, sort of mixed rates. We need some way to handle redundancies. So when there's bit errors, how do we make sure there's no dropouts? We want to support the cloud. We want to work with different switches. You might have a 10 gig switch today, 100 gig switch tomorrow, something else in the future. So we have to make sure whatever our solution is can handle these different rates. We want to have a traffic model so that it's easier to design the system. We need to support different kinds of audio, PCM audio, AS3 audio. And we want to make sure whatever system we have is very future-proof. So it can support future formats, it can support future applications, it can support different networking things. So these are different requirements that we're going to sort of assess the current state of the product, or the current state of the standards and sort of the new standards. So what do we have today? We have SDI, we have 2110, ASPEN IP Live. So let's sort of take a quick look at these and how they sort of stack up with the standards. So SDI, we've got our active video, but we also send our blanking area. In the blanking area, we have our audio. We're wasting a lot of area in that blanking area with sort of unnecessary overhead, and depending on the standard, it can become quite a large amount of sort of wasted space. When we look at SDI, it doesn't have separate essence flows, so it sort of doesn't meet that requirement. Doesn't work with sort of standard switches, and so if you go through that list of requirements, SDI, I mean, it's been great, but it doesn't meet a lot of what we need moving forward. So we've got SMPTE 2022-6. So basically what that standard is about is we take our SDI, we wrap it with RDP, UDP, and IP. We take those chunks and we put it across the network. So now we're addressing some of those requirements. We now, on a network, we can work with standard switches, but we haven't got separate flows. So all the audio, the video, the auxiliary are all lumped together, so we sort of fail that requirement. Actually, I think we have the next slide here. So other limitations, it wastes a bunch of bandwidth, doesn't have a traffic model, which can cause some grief on the network. It's, at least in the current version, doesn't support things like UHD and some other future formats. So it's definitely limited to the future, but it does do some things really well. I mean, in terms of if you're just doing sort of more longer haul stuff where you want to keep everything together, it does serve a good need, and it's a good standard. But sort of moving to the future, it has its limitations. So then we have the VSF TR04. So it basically takes 2022-6, and let's break out the audio separately. So we're going to use AS67 to basically send the audio separately. So this is now going to allow us to do applications like breakaway audio, things like that. But we still have the video and the metadata is all still together. We still got that large wasted space of the blanking area. So it's not sort of meeting all the requirements, but it's an improvement. We have other things like ASPEN and IP Live and stuff. So these are proprietary solutions. So it sort of meets that or fails on the requirement there of the, we want to have open standards. Things like IP Live, everything's still in one essence flow. So again, we fail to meet those requirements. If we look at audio, we have lots of different audio standards. There's, I can't remember, it's like 8 or 9 or something. There's a lot of different audio standards. So we have AS67, so it's done by the AS Society, so it's an open standard, so that's good. But it only does PCM audio, so it doesn't do the non-PCM and the AS3 sort of transparent mode, so it's got a few weaknesses there. You've got Dante and Ravenna, which are very popular. These are proprietary solutions, may require special hardware, so again, they sort of don't meet all the requirements that we set out. And there's a whole bunch of more audio solutions, but again, they're all sort of proprietary and they're not sort of meeting the requirements that we sort of set out at the beginning. Okay, so just a quick summary of what we've got today. Basically, none of them meet the requirements. They all do certain things well, they all have deficiencies. So there's no one solution right now that sort of meets all the requirements we need moving forward. Okay, so to address that, the Video Services Forum came up with TR03, and it was basically developed to address those requirements. And it did a reasonable job of this. It was basically trying to draw on existing standards where possible, so it didn't want to sort of reinvent the wheel. So if an existing standard was available, we would try to use it, and we'd sort of define new things. Unfortunately, this was developed by a relatively small group, so it didn't have a wide range of input. So there's kind of a limitation there. There may be things that we didn't think of that would be sort of good ideas to put into this sort of future moving standard. So that brings us then to the SMPTE 2110. So the main idea of SMPTE 2110 was basically we want to take TR03, which had lots of good ideas, was basically trying to address all those requirements that were set out, but we want to make it into a real standard. SMPTE is a standards organization, it's internationally recognized, so when SMPTE comes up with it, it's a good, well thought out standard. The committee draws, I can't remember what the numbers, we have a few hundred people that are sort of on the committee, so it's getting input from a huge number of people, it's getting input from different areas. So there's been where originally may have been more focused on sort of just video type stuff. We've had a lot of input, say, from the post-production area. So we've sort of enriched and made the standard much more flexible and more future-proof, so it can handle both the television as well as the sort of post-production in other markets. We've had lots of different vendors look at it, so we've had software vendors and hardware vendors and cloud vendors, and so we've had input from lots and lots of different companies, lots and lots of different users, and so we've taken sort of the good ideas from TR03 and made them that much better, and we've sort of gone through and sort of dotted all the I's and crossed all the T's to sort of make sure that it's kind of rock solid. And so with that, hopefully we've made now the sort of the one superpower standard. So from an essence point of view, we're going to separate the audio, the video, the metadata into 3 separate flows. So basically, we're going to send just the active video, and so we're going to wrap that up into a packet. We're going to take our audio, we're going to send that separately, and then we're also going to send the auxiliary space separately. So from a standards point of view, so the official name of the standard here is the Professional Media over Managed Networks, and it's a family. So to make it more manageable and sort of easier to use, we've broken it up into several parts. This allows us to sort of finish one part, get that published, then move on to the next part. So right now we have, I guess it's sort of 6 parts. So the first one defines kind of not an overview document, but it does the timing model and the definitions, and it's kind of sort of from higher level stuff. We then get into the video, so the dash, and we've also sort of broken up each area into certain numbering codes. So the dash 20 area deals with video. So currently we have a uncompressed video, and then we've also added a traffic shaping one, so that's the dash 21. The dash 30s cover audio, so we sort of started with the dash 30, which is the PCM audio, but we've also now have the 31, which allows us to take AS3 and allow it to be transparently transported across the network. The dash 40s family covers things related to auxiliary space, and in the future this will grow. Working with 2110 is that there's actually several standards that sort of go with it or sort of part of it. So we have the Genlock one, so the 2059, so Paul will be presenting after, so a whole bunch of information on that. And then we also have the seamless protection. So these all sort of work together to form even a larger family. Okay, so just on the essence, so we're using RTP, so real-time transport protocol. So we basically take our packets, we make an RTP packet, which we then wrap in UDP, which we then wrap in IP, and typically we put this over Ethernet. So this is all IP-based standards, so we're just sort of leveraging existing standards there. Works with sort of the IPv4 networks, but also will work happily with IPv6. And basically we're taking our data and wrapping it with a whole bunch of headers. An important part is that the receiver has to understand what it's getting, and we do this with something called Session Description Protocol, or SDP. Again, this is something which was used in other industries. It's an existing standard. And SDP it's an object. It's not a file or anything. It's just it's a way of describing something. And it describes the essence flows, and it's kind of this somewhat human readable, somewhat machine readable. So you can read it. You can see it on the screen there. It's a little bit cryptic, but it is human readable, but it's easy for machines. And so it describes things about what IP address you're using. In case of the audio here, what is the packet interval, so how often the packets are coming, what Genlock reference you have. So a whole bunch of parameters that define image size, what's the encoding and stuff is all described in this SDP object. And being a sort of a standard thing, then any vendor can all agree on this. Okay, so with the 20, the essence flows. So this was based on RFC 4175. The original hope was we could actually just reference it, because there's lots of good stuff in 4175. Unfortunately, 4175 has also lots of baggage stuff that we don't care about. So in the end, we opted to just basically take all the good stuff from 4175 and leave all the other stuff behind. Otherwise, we sort of have the standard that says, keep this sentence, drop this sentence, keep this sentence, drop the sentence, and that was just getting a little too weird. So we're only transmitting the active image. So we can support images up to 32K by 32K. So I'm hoping that will cover kind of the next generation. We got 8K coming, 32K by 32K should hopefully cover us for a long time. Also, we support all kinds of different image sizes. So unlike a lot of standards which have very fixed sizes, you can have images of any size. So if you want to transmit a little logo or a lower third or sort of other interesting applications, the standard allows that. So it can be used for a variety of applications more than just your full frame image. Supports all kinds of color spaces and pixel structures. So it's very flexible and rich that way. Has a few different ways that the packets can be sort of, or the information can put in packets. Sort of some various advantages and disadvantages of each of those. For the audio, so we base this largely on AS67. AS67 is a good standard, it covers things. We did want to sort of constrain it a bit, just because that standard has a lot of richness, and we sort of wanted to make it more easy to make it interoperable. So what we've also done in the standard is we've grouped various feature sets into these different conformance levels. So if you want to do 48 kilohertz audio with 1 millisecond packet timing, we call that conformance level A. Then we also have one, we say you want to do 96 kilohertz or different packet intervals. And so there's different conformance levels. For compatibility with AS67, any AS67 receiver can receive a conformance level A signal. So those were sort of designed to be the same. And so any AS67 receiver, if you stick to conformance level A, can receive the 2130 stream. So that makes for a lot of compatibility. As you get into some of the other conformance levels, then many AS67 receivers will work, but then it's not guaranteed. On the transmitter side, we did put some constraints on. So most AS67 transmitters can be made to be -30 compatible, but there are a few sort of constraints that they have to honor. So then we have the 31 for doing, basically allows us to do the transparent transport of AS3. So you may have AS3 signals that may have various compressed or other stuff in it. It allows us to basically take that across the system. This standard here was largely based on the AM824. Again, we're always trying to reuse standards where we can and leverage those sort of knowledge and what's already been written down. For the 40, this covers all our auxiliary space. So an IETF standard is sort of is in the process, so it's very close to being finalized. And so the -40 for the most part references that. Basically then it allows you the transport of all your auxiliary stuff. So your closed captioning and all those sort of other stuff that you find in your auxiliary space. Just kind of note that it doesn't cover the transport of the analog signals. So you have to have a digital ANGS packet. The -21 document is our timing model. It basically defines the sort of how close to perfect you have to be and the timing of your output signal. This basically helps a lot with network design, because otherwise you can have a lot of packets all arriving at the same time, which can cause congestion. So the model helps ensure a certain nicely behaved transmitters. Also simplifies receiver design, because you have to, like, how much buffering, what sort of constraints I have on my receiver. This timing model allows us to design and make more interoperable our receivers. Things that had to be considered, was very hard when we came up with the standard, was you've got hardware-based implementations which have very precise timing. However, software solutions are becoming much more prevalent. So with software, we want to support that. But with software, your timing isn't as accurate, so we have to be able to handle that. As we move into the cloud, that adds more jitter. We want to work with switches from today and tomorrow. So we have quite a wide range of information we had to consider as we were coming up with this standard. So to time everything, we've got the 2059 Genlock standards. This is based on the IEEE 1588, and it allows us to basically distribute time to every device. So every receiving device, every transmitter gets a sense of time. So everything is then frequency locked, and then using the -1 of that allows us to phase align all our signals. Paul will be giving us a whole bunch more information on that after. So the one problem was when we split our flows into our different essences into different flows, we now have the problem we have to make sure we keep everything aligned. So if we have audio coming from 2 different devices, or if I have audio and video, I need to keep everything nicely aligned. And so how do I do that? And so with the standard, using RTP timestamps, and those timestamps are locked to our PTP time, we can then realign all our signals to ensure that we have very precise audio-video alignment. And what this system allows us to do is we can compensate for delays in the network, different path delays, different jitters. So we can have signals which are coming from a long ways away or close or taking different paths. And using the tools in here with the timestamps, we can align everything. So we want to be able to have redundancy. So in an Ethernet network, it's not lossless. Packets will get dropped. We're using UDP, which has then no retransmission. So how do we ensure we have reliable reception in the end? So we're going to use the SMPTE 22-7 standard. So this allows, basically, I transmit the same information on two different paths. I construct that in a certain way. The receiver then can receive packets on either path and then basically seamlessly recreate it. This technique differs from, say, where you have a hard A-B path, because here you can lose one packet on one packet on the other, and as long as every packet is received once on one of the two streams, then you can recreate the signal flawlessly. So even though it's called SMPTE 2022-7, it's actually a very generic standard. It actually can really be used with any RTP stream, and actually we have a project in SMPTE right now where we're doing some minor tweaks to -7 to actually make it more explicitly more generic. But really 2022-7 can be used with any RTP stream, and everything we've talked about is an RTP stream. Some other nice things that actually come from using something like this technique is, say you want to take a switch out for maintenance. Well, yes, you're going to lose your redundancy, but you can actually take one of your switches down, do a firmware upgrade on it, get it all working, and then bring it back in service and do that with the other switch. So it's kind of nice that not only does it give you the protection between your lost packets, but it also helps you with your maintenance of your network, which invariably you'll have to do code updates. So control, sort of outside the scope of the 2110 standard. I mean, so as Thomas was mentioning, I mean, there's the AMWA, the NMOS 04 and 05 for the registration, discovery, and connection management are a few options you have. Okay, so where are we at? So the -10, -20, and -30 are approved standards. They're basically in the publication queue, so we can't actually say they're published, but they're very, very close. So they're just approved, waiting for the publication. We've got the other standards, the 21, 31, and 40 are very close, so they're coming soon. So to make sure all these equipment or all these standards are sort of well thought out at work, we've had several interops, and this is sort of picture I took from one of the Houston ones here. So we basically have, I guess it was like about 12 racks of equipment. We've got vendors coming from all over the planet with their equipment. We're putting it together to make sure does it work. We're testing out different pieces of the standard. So at each interop, we're sort of focusing on certain areas. Let's see here. So just some of the interops that we've had, we sort of started them back in January of 2016. And that one was actually TR03 because at that point 2110 didn't exist. We have a couple different kinds of interops. We have these ones we call dirty hands, where we have a whole bunch of engineers getting together and working through the standard and debugging it. We have some other interops where we're preparing for these showcases, which are very similar, but we're not doing as much testing of the standard and pushing the envelope. So we have different kinds. But we've had sort of several over time. I mean, earlier in this year, in February, we had another Dirty Hands event. It had about a little over 20 companies, and we were also doing the 2059 and the 2022-7. As more companies are developing product, we had another one in April and then August, and it grew up to 40 companies. And then the last one in August, we had 50 companies. So these events are becoming quite large. I'm one of the technical organizers of these events. We had 100 people and 50 different companies basically testing all our equipment together. And then early next year, we'll have the next one to sort of test some of the parts of the standard that haven't been as tested. So there's a lot of support in the industry for 2110. We've got on the AIMS roadmap is 2110. On Thomas's report, they said, I mean, they're all sort of supportive of the 2110. At this point now, we have all the functions that you need to make your station or do your application. So there's companies make gateways, there's companies that make multi-viewers, there's server companies, cameras, graphics, processing. So all the different bits and pieces you need to make, to do your application, there are companies now that sell that product. The switch vendors have been very supportive. So like at the last Interop, we had 5 different switch vendors that are all coming. I mean, they are running sort of standard code, but we're just sort of making sure that all the systems work together. And even the companies that had proprietary solutions, they're also supporting the 2110. So pretty much every company now is supportive of 2110. So we put on several of these showcase events. So we basically, to sort of at NAB and IBC, we put together these events to sort of show all these companies coming together. These ones were from IBC, which was just a few weeks ago. So we had, in addition to our interoperability area, we were also showing sort of a live production area. That was sort of a new area, because now we've got a lot of companies showing that have servers and cameras and graphics, which we didn't have at the previous event. So we've been sort of adding more and more. So this is sort of an example of a typical showcase. So we have lots of different organizations that are working together with these showcases. And actually, we have a showcase right here. So when you're at one of your breaks or at lunch and stuff over in the, I'm not sure what they call the other area, but basically around on the 5th level here in the other area, there's an IP showcase area. So we have, I think it's about 30 different companies that have come together. So we're showing various cameras and servers and multi-viewers and gateways and stuff. So you can sort of see it all live and working here. So just in conclusion here, of all the different things, 2110 meets the requirements that we need to move forward. It's an open standard. The standard is very, very close to being fully published. There are many companies. I mean, at the last Interops we had 50 plus companies, and I know at the next one there's more companies that have even expressed interests. So we have a high degree of interoperability, and I think the 2110 now will be the sort of the next superpower standard that we will have for a long, long time to come. So we have some questions. I think there I have one of the longest email addresses of anyone between the company name and my name. It's like super long there.
Hi, this is Sherban Simu. I'm previously founder of Aspera. I'm relatively new to this field, so thank you for the overview. It went great. My question is: the standards team interested or currently maintaining a reference implementation for the various substandards in terms of, or in the form of open source or reference code?
I'm not aware of any reference standards. I mean, there's lots of, I mean, every company has their own solution. There are many IP companies that sell solutions, but that's a very interesting idea, having a more open reference.
Do you think there might be an interest in the standards team to have an open reference? That way, I'm thinking things like those interop bashes can be a lot easier if there would be a reference implementation to go against and from.
Absolutely, yes. And that's something sort of as we move forward. I mean, the interops have been great, but sort of in the long term, they're not the most sustainable solution. So, I mean, I'm sort of working on a committee that we're looking at compliance stuff. So definitely that's something of interest, yes.
Thank you.
I can comment on that briefly. Thomas Edwards from Fox. Savoir-faire Linux has added SMPTE 2110-20 receivers into FFmpeg. So again, this is not things I think SMPTE generally does in terms of maintaining reference implementations, but certainly there are some open source implementations which are starting to show up. Also, if you're looking for a Wireshark dissector of SMPTE 2110 standards, we've made some available from Fox on GitHub that you can download.
Yep, and definitely if you are an implementer and working on the dissectors and stuff for Wireshark are very helpful for being able to look at your packets and make sure they're all correct and so on. Okay, thank you.